All right, let's talk about bonding. Um, First thing we want to consider about bonds, covalent, ionic, metallic, whatever, energy is required to break a bond. In order to overcome the attraction, you have to input energy to the system. Conversely, energy is released when a bond forms. It makes perfect sense. We can measure the bond energy in lots of ways to determine the strength of an interaction. First, I want to talk about ionic bonding. Um, Ionic bonding consists of ions, and they tend to be crystalline solids we're used to seeing, like table salt. And they form when an atom with a relatively small ionization energy, like a metal, interacts with an atom with a relatively large electron affinity, like a nonmetal. And that's a generic idea there, okay? Those two objects, once they have interacted and exchanged an electron or two, are then held together by their electrostatic attraction for oppositely charged particles. They form because the fundamental unit of ions has less potential energy than the separated ions themselves. So, they form because it's a favorable process, therefore, it happens naturally. All bonds that form naturally do so because the bonded form is in a lower energy state than the separated atoms or ions, and thus is a thermodynamically favorable process. Bond length, it tells us a function of the items related in a bond. It's the distance between bonded atoms where potential energy of the system is at a minimum. And we'll look at that graphically next. There are three forces we have to consider when considering why bonds are at the length they are, and that is the repulsion between protons and repulsion between electrons, and then the attraction of protons for electrons and vice versa. Um, Generally speaking, the electrons in a covalent bond, and this is when we're getting into bond length, tend to be between the two nuclei, internuclear space. But they can be theoretically anywhere within a certain zone of influence around a nucleus. Um, the configuration of electrons being between the two nuclei maximizes attraction and therefore is a very favorable position for electrons to be in a bond. And this is a graph that kind of illustrates that relationship. Um, when we look at internuclear distance being far apart, we have very little attraction or repulsion. As two atoms become closer and closer together, attraction then before protons for electrons then begins to take hold, and we reach a point where attraction is maximized, and that's when repulsion begins to become a larger factor. And then if we move atoms even closer together, repulsion becomes the deciding factor in behavior. And graphically on the left, we see some dot representations of two hydrogen atoms. As you move them closer together, how those attractive forces come together, and electrons are mostly internuclear. Polar covalent bonds occur when electrons are not shared equally. The two species involved in the bond don't interact with the same amount of magnitude of attraction for electrons. When this happens, we call it a permanent dipole. They can be non-permanent. That occurs when we look at intermolecular forces that are fleeting. But in a covalent bond, if there is an imbalance in attraction of protons for electrons, then we call that a permanent dipole, or a permanent dipole moment. You'll see those terms used a lot. This is a hydrogen fluoride molecule drawn Lewis structure, and then the symbology for the direction of electron density. There's just a basic ball and stick model, and here's a heat map of electron density where red is where electrons spend more time and blue is where they spend less time. This is just some molecules that are and are not polar. We see on the left sulfur trioxide, and then methane nonpolar. You see that there's a lot of symmetry and balance in those drawings. And when we look at them structurally in 3 dimensions, they're also quite balanced. Whereas ammonia and water are imbalanced and therefore are polar. We do a lot of bonding discussions around electronegativity because electronegativity implies the degree to which atoms are held in a bond, and so we have to keep this trend in mind where fluorine is most electronegative and francium, cesium tend to be the least electronegative. What is electronegativity? It's the ability of a bond in an atom, in a molecule to attract shared electrons to itself. We can actually calculate this the way Pauling did, and this is a method that we'll tell you about, but you don't actually have to execute academically that I know of. We have an expected value for bond energy. Um, has its own calculation, and then you use the measured bond energy minus the expected bond energy, and that's your delta electronegativity across a bond. So when we make all these comparisons, it helps us understand the degree of polarity of a bond. If X has a greater electronegativity than hydrogen, its electrons are closer to X and the molecule is polar. If they're about the same, then molecule is nonpolar. So this is just water and then water put in a electrical field, and you notice the way water orients itself with the negative pole of the water molecule attracted towards the positive pole of the field and vice versa. This is ammonia doing the same thing. What you don't see is a pair of electrons on the central atom here, but you see the orientation in space in the electrical field. This is carbon dioxide. These aren't written as double bonds, which is what they are, but you do see there is a fair degree of polarity within the molecule, but results in a nonpolar molecule because the degree of electronegative pull is the same in either direction. So the two polar bonds offset, form a nonpolar molecule. So we won't go over explicitly over electron configurations, just to say that stable compounds, atoms, are, for as far as this modeling goes, they will take on a noble gas configuration, which means that they will fill the valence shell, a S2p6 configuration. Two nonmetals are going to react and form a covalent bond by sharing electrons, and in doing so, each atom perceives it is ownership of those electrons and therefore is filling its valence shell. When a nonmetal and a group 1 or 2 metal react to form an ionic compound, ions form so that the valence electron configuration of the nonmetal is completed and the valence orbitals of the metal are emptied, both of which lead to a full outermost energy level and therefore a noble gas configuration of electrons. So generally ions form to take on noble gas configurations, and there's a few exceptions, and this is with group 1 and group 13 or 14 metals like tin, lead, bismuth, thallium. Tends to be that metals with d electrons and will lose their highest numerical energy of electrons before losing any d electrons. And there's an example there with manganese metallic and manganese 3+. You see that generally you're going to lose these outermost energy level 4s electrons prior to losing any d subshell electrons, and that's common for most transition metals. Ion size. This is one of my favorite slides. Cations are smaller than parent atoms as they are losing electrons. You have increased attraction because there's less repulsion in the valence shell. Anions are larger than their parent atoms as they are gaining electrons. You've increased repulsion by adding electrons to the valence shell. And it's just a silly mnemonic with a great picture. You're welcome for that. Monster ants and tiny cats. Kind of help you remember the size of ions if you get in a pinch. Ion size trend there illustrated graphically, just showing off that as a group going down a group, we see ion size increase. Even though you get a large number of protons with each drop down in energy level, the repulsion of each energy level for the inner layers is significant enough to be the dominant force there that dictates the trend. Isoelectronic ions, this is just an observation about electron-proton relationships, but if we take 5 atoms that are of different character but the same number of electrons in the valence shell, we see that their sizes shrink as the number of protons in the nucleus grows, and this should stand perfectly to reason. All 5 of these atoms have the same exact electron configuration but different numbers of protons, and therefore you can see that atoms with larger numbers of protons are much smaller than their isoelectric counterparts with fewer protons. The next big topic we want to discuss is lattice energy, and this is the potential energy released when separated gaseous ions are packed together to form an ionic solid, or, if we reverse that, the energy required to separate an ionic solid into its gaseous ions. We're going to look at a couple diagrams that illustrate this, so this should be familiar to you by the time we get through this part of the video. Lots of steps have to take place chemically to illustrate the energies that are exchanged going from ionic crystalline solid to gaseous ions. So let's take a look at a Born-Haber cycle for sodium chloride. what you see at each phase of this is a particular interaction or chemical reaction where something is changing phase, and we have to account for each step so we can calculate the lattice energy of this crystal structure. So each step counts as some particular step. Usually what you see done first is the opposite of a heat of formation. And what that does is goes from crystalline solid to ions or atoms in their standard state, sodium being a solid, chlorine being a gas. And since you have 1 mole of chlorine in this formula unit, you'll have half a mole of chlorine gas, which is the standard state of chlorine. The next step, we see sodium going from solid to gas, which is called sublimation. That has a certain energy value. And then the next step, we see sodium gas to sodium ion in gas form, which is ionization energy. In the next step, we are moving our attention to chlorine. We see that chlorine is going from chlorine in the gas phase to chlorine atoms, and it's still in the gas phase. And that's called atomization, or breaking the diatomic bond. It's essentially cleaving the bond, the diatomic chlorine bond, to form chlorine. Notice that you have half a mole of chlorine in gas form diatomic here, and once you split this half a mole of Cl2, you have 1 mole of chlorine. The next step is going to be variable. This is the ionization, or the activation. Sorry, this is the electron affinity of chlorine, and notice that it's exothermic. Electron affinity is often exothermic, but it can also be endothermic. And so in this case, it's going downward. We see the negative energy. We see a release of energy when this atom binds this electron. Once we've completed all those steps, now we have an energy differential that explains the lattice energy of our structure, and that's this value here. Okay, and all these are added up. Note that this one was reversed because we are not forming the salt, we are taking the salt apart. So we really will flip the sign on 411 and turn the arrow around. And the reason these arrows have their own orientations is because they come from shelf values. They come from tables, and sometimes they're not going the way we want them to go for our whatever investigation we're doing. Anyway, so we see our energy inputs are going upward and our energy outputs are going downward, and the difference is lattice energy. Okay. So we can also represent lattice energy in terms of Coulombic attraction, and this is a very important formula for you to have understanding of. Is generally the lattice energy is a function of two things. It's a function of the magnitude of the positive and negative charges and the radius of the molecule, or radius of the bonds. So K is a proportionality constant, and we can sort of ignore. Lattice energy generally is expressed as a negative value as energy output when the bonds form. Attractive forces between pairs of oppositely charged ions increases with increased charge of the ions or with decreased ionic sizes. So we're looking for things that make radius go down and things that make charge magnitude go up to impact our lattice energy. It's important to have a basic idea here that there's no such thing as a totally ionic bond. There's something called percent ionic character, and that's a function of the degree of pull across a bond. And we won't discuss percent ionic character explicitly, but it is a relevant topic going forward in your chemistry learning. It just won't be a part of this course. Essentially, as you increase electronegativity difference, ionic character increases. That doesn't mean it's an ionic bond, but the ionic character increases. Compounds of more than 50% ionic character are considered to be ionic. So you might be asking, well, how do you calculate ionic character? And the short answer is you don't need to worry about it in this course, and there's nothing will be quantified. We'll leave our definition of ionic compound to a cation and an anion that come generally from a metal and a nonmetal, or ammonia and a nonmetal. Keep in mind that polyatomic ions are held together by covalent bonds. So even though sodium sulfate is an ionic compound, it's got 4 covalent bonds in it. This is my one slide dedicated to the crystal structures of ionic compounds. We don't study crystal lattices. They're super neat, and if you like organization, they're very fascinating. But this is lithium fluoride. This is a typical type of crystal, a cubic set, and we won't bore you with the details. I just wanted to show you a neat picture. Here it is in terms of lattice energy. This, if you don't ignore the words overall change here, we're just looking at another lattice energy. This energy value right here is heat of formation. Note you have elements in their standard state then becoming the crystal there. So this is heat of formation, step 1. Then step 2 is sublimation of lithium. Step 3 is ionization of lithium. And then step 4 is going from fluorine and gas diatomic to fluorine atomic. And then finally, your active electron affinity of fluorine for its electron, another exothermic. And then here is our lattice energy. This is just a comparison to show you the difference between magnesium oxide's lattice energy and sodium fluoride's lattice energy. Huge difference, and that is generally speaking of the difference here has to do with the magnitude of charge, 2 and 2, for I'm going to put an E here for energy since it's not force. The two values are +2 and -2, so it really impacts the magnitude of our numerator, making our lattice energy larger. And that's an important feature of the differences in the different types of salts. Here's a table showing you the same thing. Here's the magnesium oxide value we were just looking at compared to, what was it? Sodium fluoride. Well, sodium fluoride is here. You can see four times as large, having bigger charges. So this table, though, you can make sense of why each of these has the lattice energies it does. Pause and take a look if you like. And finally, I want to talk about bonds just in terms of ionic compounds. Bonds tend to be a model we create, the term bond, and the way we draw them and show them. We have two giant models we'll talk about in a few minutes that help us understand what bonds are, but they're all constructs of our ideas. One thing we need to note before we go any further is that each bond is one electron domain. In other words, it's one group of electrons. This is one bond, a single bond. A double bond is one bond. A triple bond is one bond, even though there are multiple pairs of electrons there. We'll sometimes call double and triple bonds multiple bonds. On the next page, we're looking at bond length as it pertains to bond energy. And so what we see on the left-hand column is the bond, and then the length in nanometers between the two nuclei. And this would be great for you to apply that idea that as we build multiple bonds, we see the bond length decrease and the energy increase. So it's worth your time to look through that data for just a moment. Then it's also important that we understand how bond energy can be used to calculate delta H in a reaction. We will use tabular data or data from tables to find the bond energy of hydrogen, oxygen, and water, and then we would use this formula, the sum of the energies of the bonds broken, which would mean reactants, minus the sum of the energies of the bond formed, which would be products, to determine the overall delta H of this process. We used to do this in thermo with data for heats of formation. That's different. It's products minus reactants. Well, when we're doing energies of reaction based on bond energy, it's bonds broken, which is reactants, minus bonds formed, which is products. And that makes sense. This is energy input, and this is energy output. So we want that to have a negative sign, and we want this to have the positive sign. So this stands to reason also. So I mentioned two models we have to consider. Everything you've learned up until now in AP chemistry and even introductory chemistry has been the localized electron model. In other words, electrons belong to an atom. But there's a much more complex, much more in-depth method of determining electron positioning based on their molecule they're on rather than just on the body they came with, and that's called the molecular orbital model. And we'll look at that in a little more depth at the end of the unit. But essentially what it applies to is electrons occupy orbitals in a molecule much the same way that they occupy orbitals in atoms, is they don't really apply to one space. Once there's a degree of attraction for all the particles there, the electrons are essentially grouped around the entire molecule. They're not restricted to one atom. Whereas our localized model, which is what we've learned up till now, is that molecules are composed of atoms that are bound together by sharing pairs of electrons using atomic orbitals of bound atoms. It's a pretty straightforward and easy to learn model, and that's why we use it. But again, it's just a model. There are some terms that it's important to us to remember in localized model, which is what we need to talk about. Is the lone pair is a pair of electrons on an atom that are not bonding, and then a shared or bonding pair is electrons that are in space between atoms, and their position in space has to do with the attraction for each atom. We'll use Lewis structures to draw the structures we see in covalent, mostly covalent drawings. We'll see a few ionic perhaps. We have to keep in mind that when we do this, we're achieving noble gas configuration for each of the atoms involved. And this was on the last slide too, but ionic Lewis structures, to spare you, keep in mind we have to draw each ion in brackets with its charge after the bracket to indicate that it's an ion. Covalent Lewis structures, remember that we will simply draw them with ball and stick models with pairs of electrons around the central atom. And that brings us to the end of the first video on bonding.